Hey everyone, it's Luke Monington, and in today's video, we'll be discussing the evolution of deep learning through its three major eras and uncover the key ingredients that propelled AI to new heights during each period. After that, we'll jump into the fascinating realm of large language models, taking a closer look at what drives them and the secret sauce behind their incredible success. As we talk more about these incredible models, we'll also tackle some interesting questions like, do large language models really know anything? How do they compare to humans when it comes to knowledge and communication? And do they actually possess reasoning abilities? To wrap things up, we'll discuss the importance of fine-tuning these models to make them even better and more aligned with our needs and preferences. So sit back, relax, and let's explore the amazing world of artificial intelligence and deep learning. And if you enjoy this video, don't forget to like and subscribe for more informative content. The evolution of machine learning can be delineated into three distinct periods, each characterized by specific developments and growth in computational capacity. These three periods are the pre-deep learning era, the deep learning era, and the large-scale era. During the pre-deep learning era, from 1952 to 2010, compute for training machine learning models expanded according to Moore's law, experiencing a doubling time approximately every 20 months. In this time, advances in computing technology were primarily driven by improvements in hardware and transistor density. A significant shift occurred around 2010, marking the beginning of the deep learning era. This period witnessed an acceleration in scaling of training compute with a doubling time approximately every 6 months. The advent of deep learning techniques revolutionized the field of machine learning, as neural networks became capable of processing vast amounts of data and handling complex tasks. In this era, machine learning systems made significant strides in areas such as computer vision, natural language processing, and reinforcement learning. While many people believe the deep learning era began with the creation of AlexNet in 2012, the evidence suggests it may have started as early as 2010. A major factor in the deep learning era is the shift to larger models and improved performance. It's important to note that before AlexNet, other models were already exhibiting some of the key features typically associated with deep learning. These models boasted large sizes and depth, achieved remarkable performance gains, and even utilized GPU-based training for greater efficiency. The existence of these models prior to AlexNet indicates that the wheels of change were already in motion. Whether it started in 2010 or 2012, one thing is certain. The era of deep learning dramatically transformed the world of AI, opening up new possibilities and shaping the technology of the future. Finally, the large-scale era emerged in late 2015, bringing about a new trend in machine learning, the development of models with a 10 to 100-fold larger requirement in training compute. The rapid growth in computational demands during this era is indicative of the increasingly intricate models being developed, which exhibit unprecedented capabilities in a variety of domains. Next, I'll be discussing large language models, which are the cornerstone of the large-scale era. The intersection of technology and philosophy as it relates to large language models is explored more in this research paper. In recent years, LLMs such as GPT and Palm have revolutionized the field of AI. These models, built on transformer architectures, consist of hundreds of billions of parameters and are trained on vast amounts of textual data. The impressive performance of these models is due to three key factors: the scaling performance with training set size, qualitative leaps in capability as the models grow, and the reduction of numerous intelligent tasks to next token prediction. So what exactly do LLMs really do? Well, LLMs are fundamentally different from humans in their use of language. While human language is rooted in social context and interaction, LLMs are generative mathematical models that predict the statistical distribution of tokens in human-generated text, including words, phrases, and punctuation marks. To better understand LLMs, let's consider a few examples. When given a prompt such as "the first person to walk on the moon was," an LLM might respond with "Neil Armstrong." In this case, we are not directly asking the model who the first person to walk on the moon was. Instead, we are asking which words are more likely to follow the given sequence according to the statistical distribution of words in human text. Similarly, when prompted with "twinkle twinkle," the LLM will likely respond with "little star," predicting the most statistically probable continuation of the text. These examples illustrate that LLMs do not truly know or understand language like humans do. They simply generate statistically likely sequences of words. Now let's delve into a comparison between humans and large language models in terms of processing and answering questions. Let's take a look at how a human, such as Bob, responds to a question. When Bob answers a question, he takes into account the context, the person asking, and the impact his answer may have on that person's beliefs. He can also rely on various external sources and methods, such as direct observation or consulting references, to verify the accuracy of his response. This shared understanding of truth allows humans to engage in meaningful conversations. Now let's turn our attention to LLMs. These AI systems differ significantly from humans in how they process and answer questions. While LLMs aren't inherently conversational agents, they are embedded in larger systems and fine-tuned to generate dialogue-like responses. An LLM generates responses based on statistically likely sequences of words when given a prompt, which may not necessarily resemble human conversation patterns. In order to produce conversation-like responses, LLMs are often prompted with prefixes that guide them towards the desired output, such as emulating a dialogue. The ability to adapt LLMs to perform various tasks without additional training has led to a growing area of AI research known as prompt engineering. This field focuses on designing prompts that effectively guide LLMs to produce the desired outputs. However, this approach is a stopgap solution until we develop better models to understand the relationship between human language and intentions. As we compare humans and LLMs, it is essential to keep in mind their distinct methods of processing information and the role of context in shaping their responses. So, with this all in mind, do large language models really know anything? To understand this answer, we must first examine the fundamental question of LLMs. They are primarily designed to generate statistically likely continuations of word sequences, regardless of the context or intention behind these sequences. This versatile capability enables LLMs to perform various tasks such as summarizing articles, translating languages, or solving puzzles. However, it is essential to recognize that LLMs only perform this singular function. Now let's compare LLMs with humans in terms of communication and understanding. Unlike humans, a simple LLM-based system has no communicative intent. It doesn't know or understand that it's interacting with a person, or that its responses impact a person's beliefs. Furthermore, LLMs don't possess beliefs in the way that humans do. For instance, an LLM may generate a response, but its prediction simply reflects the likelihood of word sequences. So, when we consider the larger context, a simple LLM-based dialogue system doesn't have the beliefs in the same sense as humans. It may predict and generate sequences of words that appear to convey knowledge, but it doesn't understand or participate in the human experience of truth and falsity. Now let's discuss whether LLMs actually have the ability to reason. First off, we need to understand the nature of reasoning. When founded in formal logic, reasoning is content neutral, meaning that its validity doesn't rely on the specific content of the premises. But can LLMs really reason in this sense? It's a challenging question to answer. For instance, if we prompt an LLM with, "All humans are mortal and Socrates is a human, therefore," we're not instructing it to perform deductive inference. Instead, we're asking it what words are likely to follow a given sequence based on the statistical distribution of the words in the public corpus. A good answer would be, "Socrates is mortal." But things get trickier when we're dealing with more complex reasoning problems that require multiple inference steps. LLMs can address multi-step reasoning problems without additional training, thanks to clever prompt engineering, such as the chain of thought prompting technique. This involves providing a prompt prefix that contains examples of multi-step reasoning, encouraging the model to show its work and improve its reasoning performance. It's crucial to remember that the question posed to the model is still fundamentally based on predicting the most likely sequence of words to follow the given input. The model's ability to provide arguments with multiple steps, which are often valid and correct, is impressive. To some extent, a suitably prompted LLM appears to reason correctly by mimicking well-formed arguments found in the training data or the given prompt. But could this ever match the reasoning powers of a hard-coded reasoning algorithm, like a theorem prover? We're not sure yet. So, while LLMs have demonstrated remarkable capabilities, especially when prompted effectively, we should proceed with caution when characterizing their abilities as genuine reasoning. So, what does it mean to fine-tune an LLM? It's important to know that most LLMs are fine-tuned after their initial training on a textual corpus. This fine-tuning can involve supervised learning on a specialized dataset or reinforcement learning with human feedback. Fine-tuning with human feedback is especially powerful, as it can help tailor the model's responses to better match user norms, reduce harmful language, enhance factual accuracy, and prevent fabricated information. So, How does this fine-tuning impact our understanding of what LLMs actually do? Well, it doesn't change much. In the end, we still have a model that generates text based on the distribution of tokens in human language, but now it's been slightly adjusted to reflect user preferences. When we use a fine-tuned LLM, we're essentially asking a slightly different question. Given the distribution of words in human language, which user-approved words are most likely to follow the given sequence? If the fine-tuning process involves raters who prefer neutral responses, then the generated text might be more neutral. If the fine-tuning process involves raters who prefer more extreme responses, then it would be more extreme. Think of an LLM fine-tuned with human preferences as a raw model that has been trained on additional text written by raters or users. Essentially, fine-tuning LLMs helps to tailor their responses to better fit user preferences, which ultimately improves their overall performance. And there you have it. We've explored the captivating journey of deep learning through its three transformative eras and delved into the world of large language models, uncovering the factors that contribute to their phenomenal success. As we continue to make advancements in AI, it's crucial to remember the lessons learned and incredible progress made. Who knows what new breakthroughs might lie just around the corner? Thank you so much for joining me in today's discussion. If you enjoyed this video, don't forget to hit the like button and subscribe to stay updated on future content. Feel free to share your thoughts and questions in the comments below, and let's keep the conversation going. Until next time, take care and stay curious.